So as time goes on and people realize that the astrophysics community has no idea how stars evolve or how planets form, it's the same process. We begin to see that the universe is a very, very weird place at first, but then as time goes on, you realize that it's all starting to make sense. Hi, Celeste. For this talk, I want to discuss the formation of life. Now, I know Eric was mentioning to Baz, or Baz was talking to Eric. I sort of kept out of it for a little bit because I'm pretty much overwhelmed with school and work, and I have a new family now, and I've been putting my priorities with that now. But I mean, I still think about the theory a little bit, but for the most part, it's just too overwhelming to talk about most of the time. I just sort of have laid back on thinking about it because it's just too mentally overwhelming. But I did get a request from Baz to discuss the formation of life. Now, before you get into the formation of life, you have to understand how much false information is being taught by the dogma. The number one rule of stellar metamorphosis is that what you see is not always what was always there. For instance, appearances can be deceiving. The dogma says that the Earth, when the Earth formed, it stayed as its current size for billions of years. That's incorrect. What is actually true is that Earth was vastly more massive in its past, and it evolved and lost its energy and mass as it evolved, meaning when Earth was very young, it was star-like. It was like the sun. And as this Earth evolved, it cooled and collapsed gravitationally upon itself, and it created a core in its interior, forming the planet. And the true size of protoplanets is very important to understand. And this is before we get into the formation of life. There are four main principles when it comes to the formation of protoplanets, young planets. The energy and mass dissipation principle, meaning protoplanets start out incredibly hot and massive and eventually cool down to the lowest energy state and lose the majority of their mass. This means protoplanets are in no way rocky or metal objects that have only fractions of the masses of small moons. The dogma says to create something Earth-like, you started out with a bunch of smaller rocks that clump together in the vacuum of outer space. That's total nonsense. To form something as massive as the Earth, you needed to have an even larger object forming it. Rocks and minerals just don't clump together in the vacuum. That's absurd. That's like going down to the beach and taking a bunch of beach sand in your hands and throwing it up in the air and expecting the beach sand to clump together into a large rock. That doesn't work like that. You don't form things the size of the Earth without something forming the object that was much larger than the Earth itself. And we know this because we have observational evidence of all the young hot Earths that were much younger in the past, much larger, much brighter, that have collapsed, or that are currently collapsing and forming the planet in their interiors. So essentially, you have to form something as large with as much low energy material, such as rocks and minerals. You had to have started out not only with a larger object, but with an object with this material that was at a much higher enthalpy, which means it was much hotter, vastly hotter. And then I have the plasma to rock and metal principle. Protoplanets start out as plasmatic, and then cool, become denser, and become rocky and full of metal because they lose all their lighter elements, the hydrogen and helium. The foundational structure principle. This means that any object that has a differentiated interior was a much larger object in its past and places the possibility that impact remains, and many dwarf planets and planets can be classified by an internal physical understanding other than orbits or current size. And that's very important to understand too. The foundational structure principle means that if you have a large iron nickel core in the center of an object, chances are it's extremely old and had the time to form that extremely large metal, usually iron and nickel core. Earth's iron and nickel core is an alloy in the center of the Earth. If you do some calculations concerning its volume, it's around 1 billion cubic kilometers of iron nickel alloy. That is a lot of metal to melt down and to condense into the interiors of an object. The only thing that can do that is a star. That doesn't happen in the vacuum. There's nothing in the vacuum to heat up that much metal. It has to have happened inside of a star's interior. And that's exactly what happens. We observe them every single night. If it isn't cloudy, that is. The accretion principle, that's number 4. Only objects with large surface areas and gravitational fields can accrete matter. This means protoplanets have to be really, really big. The vacuum, the outer space, there's a lot of space in outer space. Everybody knows that. If you're gonna clump material together, chances are it's gonna be separated by large distances with other material. Now, how is it that you can form something as massive as the Earth when most of outer space is vacuum? Well, you use the properties of a young star to collect the material. The young star has a huge gravitational field and it has a very large surface area. So when it goes through outer space, it collects up all the remains of all the dead stars, and it collects that material in its center and it recycles it like a recycling machine, interstellar gas recycling machine. And then it forms a new planet with that material. It's very simple to understand. Large gravitational field to pull the material in, and a large surface area to actually capture it so it doesn't go anywhere. And that being said, this leads into the formation of life. And it's very simple to understand. I'm surprised astronomers and geologists and biologists, as the days progress, I'm more and more surprised that they haven't figured this out already. I don't know, maybe they have and they're not allowed to speak up about it. It's like the elephant in the room. You have a big elephant in the room, nobody can talk about it. Like, shh, As stars evolve, life evolves on them. And as they die, the life dies as well. The chemical reactions necessary for the formation of life, from the formation of molecules, from ionized plasma to polymerization of the molecules. That means you take the molecules and you combine them together to make longer molecules. Think glucose and glucose chains, long chains of glucose to form carbohydrates. To prokaryotes, to eukaryotes, and then to multicellular life, to sea plants, then to animals and land plants, all results in a series of stages of a single star's evolution. As the star evolves, different stages of life occur inside that star. Now, it might look like a centimeter or an inch right here, but this little area right here, the green zone, after, the star, quits shining after brown dwarf stages, this little green zone right here is where the life really kicks off. The very basics start forming. The elements combine into more and more complex molecules, and they mix in the atmosphere, the very thick, very different atmosphere of that young star as it evolves. It posits that stars obey the mass energy equivalence and the conservation of mass, in which stars that radiate and lose their mass to solar wind and flaring will do so because they are not thermodynamically closed systems. This means that stars that are radiating the most are losing the most mass the fastest, and old stars, called black dwarfs, do not lose any appreciable mass because they are not radiating as much. Well, clearly the Earth isn't radiating nearly as much as the sun is. It's very, 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 very old, 4.5 billion years. As well, the heat capacity of the Astron's atmosphere changes as it evolves, leading to increased or decreased rates of both chemical synthesis and energy loss to interstellar space from photoevaporation and internal convective radiative heat loss. So basically what that means is the more atmosphere you have, the more chemicals you have to move around, the more chemistry can happen. It's that simple. With the Earth's current atmosphere, It's very thin. It's mostly hydrogen and nitrogen. And chemically, sure, there are things happening, some weathering, that kind of stuff. But when it comes to the real mixing, the real meat of a star's evolution when it was younger, it's basically a finished product. You have us walking around. It's done the majority of its evolutionary processes when it comes to life. Now, when you look at Jupiter, for instance, and the Juno spacecraft has been taking some pictures of Jupiter's atmosphere, just take one look at that thing. Can you see all the chemistry taking place? You can just look at it and tell there's a hell of a lot of chemistry taking place. The clouds, they're all sorts of colors. They're huge storms. And that's just on the surface. Can you imagine what it's like all the way into the interior? That must be a hellish world. And you know there's lots of chemistry happening. There's lots of things going on in there that that will lead to the formation of life. Because similar to the Miller-Urey experiment, where they took, hydrogen, oxygen, nitrogen, and what's the other one? I think carbon. And he put it in a flask or something, and he heated it up, and he collected the material, and he could form amino acids from it just by introducing a spark and some heat. And the amino acids form naturally. Can you imagine how many amino acids are forming inside Jupiter's atmosphere right now? A whole hell of a lot of them. Yet when astronomers look at Jupiter, they're like, oh, it's just a bunch of helium and hydrogen gas swirling around. Nothing to see. It's a very myopic, it's a very short-sighted view. I guess they're still kind of scared to talk about life in other places in the galaxy, which really isn't all that scary if you think about it. I guess they're more scared of what their peers would think of them, so they keep quiet. The Taylor threshold, I don't know if Eric knows about this. Baz, you know about this. It was mentioned that by Baz Taylor that life could have existed on the moon. A threshold for the formation of life given it enough time to evolve on any individual star is presented. In short, the star had to have evolved on long enough time scales to host life. This is very, very, very important. Astronomers, they dropped the ball a long time ago. They have no idea what they're talking about. When it comes to life forming, you have to have had something evolving alongside the life forming as the life was evolving itself. It isn't the planet forms and then the life evolves on it after the fact. No, the planet and the life evolve together. It's a parallel process. So naturally, when they're looking at all the young stars that shine, and some brown dwarfs and some red dwarfs, and they're looking at large exoplanets, which are highly evolved stars, intermediate age stars, they're kind of taking the sterile viewpoint of it. Well, we have to see an actual Earth-sized object, and then we can figure out if the chemicals that are needed to form life are actually being formed on that object. No, they're forming right in front of you. That's what's happening. When you have simple molecular synthesis, when you have simple hydrogen connecting with oxygen, making water, and you have those types of reactions happening, that's the beginning of life. We're composed mainly of water inside of our own bodies. So when you see water forming, boom, there you go. It's already started. It's already beginning. And that's just one type of molecule. You have things like methane too, which is one carbon and I think 4 hydrogen. And hydrogen, gosh, stars have lots of hydrogen, You can form lots of methane, you can form lots of water in a star. Of course, a lot of it, decomposes and gets ripped off, but it keeps a lot of it as well. Okay, and the Taylor threshold, on this graph here, I had made a talk earlier. When you evolve a star, if it evolves too fast, if it loses its mass too fast, and it falls below that red line right there, that's the threshold line. So for instance, say you have a Jupiter, or a hot Jupiter, so to speak, and it's young, it's forming the beginning molecules, and somehow it gets adopted by a much larger blue giant star, and it orbits really, really, really close. Well, what's going to happen is that Jupiter is going to get ripped apart way, way, way too fast. So when it's trying to form these more and more complex molecules as it's evolving inside of its interior, it's going to be ripped apart too fast, faster than the molecules can form. So what's going to end up happening is that Jupiter is going to fall below that threshold line, and it's going to go into this yellow zone where no life will be able to form on it. And it's just going to keep on evolving down here, and it's going to permanently stay below that little red threshold line. And it's very important to understand that too, because what it means is there is a great possibility that we have an explanation for, okay, we have an Earth. Earth evolved clearly slow enough to form life. But there is also a possibility that there are objects out there like the Earth, Earth size, that were captured by a larger star, ripped it apart, but then on other stages it did the normal route and evolved slowly to where it could still form water oceans. But then what happens is it ended up being a very sterile world. So there's no life on it at all, but it will have oceans. And that would be a very weird world. And I'm pretty sure that there are probably lots of those in our galaxy as well, ocean worlds that didn't form any life. And if there is a little life, maybe it's just a few a bit of complex molecules, not up until virus, not to virus complexity or bacteria complexity, but maybe some organic molecules is on it. But for the most part, it would be completely sterile. That'd be a very strange world. Yeah, and the majority of a star life, so to speak, I guess we could classify as being when it's actually hosting life. If you want to give it a more of a life-centered viewpoint. I mean, you don't exactly have to, but I mean, in essence, this theory is saying that the life on the star is the star itself. Like coming out of the star, it's the star that forms the life on it. All that energy is dissipating and becoming more and more complex. And we're basically star children. We are children of the Earth. The Earth made us from its extreme energy in its past. And it was eventually, it was dissipating its heat and its light. And the leftover heat and light and the material that was combining together just stayed, and it gravitationally collapsed on itself, and it just became more and more complex, eventually forming, us. And it's pretty wild to think of stars in the night sky as being able to do that, because we're sort of, oh, it's just a dot in the night sky, it's nothing significant. And the best way to look at this is to realize those objects are very young. They're not billions of years old like the Earth is. The Earth is billions of years old. Those objects up there, the astronomers are wrong. They're not billions of years old. They're millions of years old. And they have an extreme amount of time to evolve, or have billions of years of more time to evolve before they can get to the point to where they can actually stabilize and they're hospitable to life and they don't have a toxic atmosphere and the gravitation is just right and the pressure is just right and the temperature is just right. I'm going to keep on going just a little bit more here. And then you have a concept called self-sterilization and host sterilization. And this is very simple. Self-sterilization means if you have a young hot star, there's no life going to be on it because it's just too hot. It's like an oven. It will just burn everything away. But it gets to the point to where the atmosphere becomes less toxic and it becomes hospitable to life eventually. With our walking on the surface and breathing in the oxygen and stuff like that. And self-sterilization happens in the early stages of the star's evolution and in the late stages of the star's evolution. So the star eventually loses its atmosphere and it becomes like a vacuum, so it can't, keep volatile elements on it. The elements just boil, or the molecules and elements just boil away, like water. When water's in vacuum, it boils away. That we have to have a certain amount of pressure to keep it in its liquid form on the surface. And self-sterilization happens with like Venus, when the carbon dioxide feedback mechanisms, the carbon sinks disappear as well when the oceans evaporate. That carbon sink is no longer there, so the carbon just builds up in the atmosphere and heats everything up, and it acts like a thermal blanket and just sterilizes everything on the surface. And then you have host sterilization, where say if you had like an Earth-like object like us, and somehow some freak accident happens and like a Jupiter-sized object comes flying into the solar system and knocks us out of orbit with the sun, or even scoots us way too close to the sun, and the sun sterilizes the surface, I guess we'd have to move underground or build some very large spaceships and get the hell out of here. But hopefully the astronomers can find a rogue Jupiter before it gets too close and causes something like that. It's kind of freaky to think about. All of humanity, all of our wars, all of the really nasty stuff we went through will be all for naught. We suffered all that time for nothing just to have some rogue Jupiter come in and knock us out of orbit or put us closer to the sun. But anyways, I think I made this talk long enough. The theory is actually pretty massive, and I just want people to know it isn't that I don't want to talk about it as much too. It's just I can't remember all of it. And people say, well, because you don't participate in online forums and you don't talk about it with people, or you're skirting people's questions or hard questions and things. It isn't that simple. I can't remember all of it. I mean, this theory is huge. It's far. I mean, yeah, sure. I thought up a lot of the ideas concerning it, but it's just a massive theory that I can't remember all of it. I mean, sure, I can remember some basics, but to go over every detail of everything that I said over the past 8+ years, come on, man. I mean, it's like asking a business owner, as the business grows and then he has like 1,000 employees, to be able to recite all the employees' names by heart. Like, are you kidding me? I mean, sure, he could probably do that when the business was first starting and he knew like 5 people who were working for him. But then the business grew, and you can't remember all those people as the business grows. You have to sort of, delegate a little bit and let other people start working on it. And I think it's really reached that point to where I have to let people start working on it. I mean, I got a lot of the basics down, and there's going to be a point to where I'm not going to be here anymore. So unless people start working on it, I guess I don't know what to say. All right, you guys, today is March 8th, 2020.